Welcome to Chem 2. This is Chapter 12, and we're going to start, there's two topics in Chapter 12, and the first one will be mass spectrometry. I do note that there are some websites here, links to websites in the PowerPoint, but I also have them linked in Canvas. All right, so let's start with the overall what we're getting into. And that is how to determine unknown compounds. So often, if you're given a compound, either you're creating it in lab or you're given one in lab, and you're trying to find out what it is. So organic chemists have a variety of techniques to do that. The first one, which I said we're going to talk about, is mass spectrometry or mass spec. There's three others: infrared spectroscopy, which is in the next section. NMR, nuclear magnetic resonance spectroscopy, which is chapter 13, and then ultraviolet spectroscopy, which is chapter 14. And each technique brings a different piece of the puzzle to the problem. You can see here that there's a link to this website. I'll also have that in Canvas. So let's start with mass spectrometry. A mass spec is a useful technique for measuring the molecular mass of any compound, and then also for getting information on the skeletal structure of a compound by identifying fragments. Okay, so here's what happens when we run a mass spec. The sample is put into the sample cell, and it's vaporized, and then it's bombarded by a stream of high energy electrons. So this is what this is showing. The electrons are bombarding this molecule. And what it does is it will convert some of the molecules to ions. So what it does is kicks another electron out of the molecule. And so it creates what's called a radical cation or cation radical. So it's got two things going on. It's lost an electron, so it doesn't lose an electron the way that often it does in a reaction. When it loses an electron, in this case, it has an odd number of electrons. And so that's what the dot indicates, that it's a radical, odd number of electrons. But it also becomes positive because it's lost an electron. So it becomes a radical cation radical. And then also, because this bombardment is so energetic, that often will fragment into smaller pieces, and at least some of the particles will retain the positive charge, and so they'll also be able to be collected and documented. All right, so here's what a mass spec looks like. So here we have the sample inject the sample, and it heats it, vaporizes the sample, and then it's bombarded by electrons. And so then we have these positive the radical is not so important. I mean, it is a radical because it loses the electron, but it's the positive charge that's important, because what it's done then is it's sent into a magnetic field. And so the positive charge is attracted to the magnetic field, and so that's why it bends around like this. It's being pulled toward the magnet. Well, because each particle is a different size, the smaller particles will bend more. So they'll come around the corner and bend more toward the magnet, and the heavier molecules will kind of do more of an outside bend, and so it will bend less. And so you can see here that you get at the detector, you get different, each molecular weight will be bent a little bit differently, and so you'll be able to separate the ions out to get the different weights. So the heaviest will be over here, and the lightest will be over to the left because it's bent the most. And so this sort of shows it from a different angle. So here's the ion source, and when it gets bent, the lighter molecules get bent the most, the heavier ones get bent the least. And then depending on how the detector's set up, you might get all of them at once, or the ion collector may scan through and collect the different ones. And so it's, first we'll collect the lighter ones and then the heavier ones. But anyway, what you end up with is a spectrum that will show the different masses. And so this is what a mass spectrum will look like. And they get lots of different patterns. A couple of things to note, let's see, is that usually they take, let's see, so on the x-axis is the mass. Well, mz means mass per charge, or m per z, m per z, mass per charge. And so that's basically the molecular mass of the particle or the compound or the particle. And then intensity is on the y-axis, and that just says, you know, how much of the molecule will be, or how much of the sample will be at that weight. And so you can see that here CO2 has a mass of 44 grams per mole, or AMU, 44 AMU. And in this case, so you can see here that's 44. So in this case, most of the carbon dioxide comes through fully intact. So the majority of the molecules just get ionized, and then they come through still as CO2. But you can see that there's a few little fragments here. So some of them have broken apart. I'm not sure what this one is. I was kind of trying to figure it out earlier, but here this one's at 16, which would just be an oxygen molecule. So one oxygen broken off. So I guess 44 minus 16 would be 28. So that'd be like a 6. Yeah, I guess that would be an oxygen and a carbon. 16 and 12 is 28. So that's what that is. So here maybe one oxygen was broken off, and then here the carbon was broken off. And if we went down this way, we may see one at 12 too, where the carbon is. But the majority has come through intact. Propane, which also has a mass of 44 grams per mole. This one's a lot different because, of course, that's C3H8. And so, again, it's got the M, and we call this the M plus peak, which we'll talk about in just a second. But the highest peak is 44. That's the complete molecule coming through. But you can see that it's also gotten some fragments. So actually, there's one at 43, which means that a hydrogen has broken off. You can see here there's a tall one at 29, and that's an interesting one because if you take 44 minus 29, you get 15, which is equal to a CH3 group. And we'll go into more of these examples in a second, but carbon is 12 plus 3 hydrogen is 15. So that's often a loss of a CH3 group. And so what this 29 will be then is C2H5. And it'll have broken off that particle. So that's what we're talking about. You start with something big and it breaks off into smaller pieces. Cyclopropane is slightly different. It's C3H6 because of the ring. And so you can see here it has a molecular weight of 42. And so that'd be right here. And so still the majority of the molecules come through full, but then there are some smaller peaks, and we don't look at every single small peak. We're just going to look at some of the bigger ones. Like here's the one at 21. This is at 27. So again, that's a loss of 15. So that's a loss of a CH3 group. Anyway, we'll look more into this. So just what I kind of was talking about on the last slide. The tallest peak is called the base peak, and it's assigned 100%. So if you notice on the last page, sometimes the mass peak is the same as the parent. Well, let's talk about this. There is often a peak that corresponds to the unfragmented cation radical, and that's called the molecular ion, or it's called the parent peak. And so it's usually given the symbol M+. So we could have the base peak is the tallest peak, so it doesn't necessarily have to be the molecular ion, but sometimes it can be. And then we have the parent peak, which is the heaviest peak, the one where the hydrogen, where nothing has been broken off, and it's the molecular weight of the compound. See the word usually. Sometimes the molecular ion peak is totally unstable and will break apart. So you don't always see it, which is a shame because that can give you some good information. So here's kind of what I was talking about. So you start with a molecule like ABC here, and you bombard it with an electron. So you're hitting it with electron. Again, sometimes you'll see it written like this, electron like that, rather than over here. And so it kicks another electron out. So that's why you see two over here, because the one that got sent in and then the other one that broke off. And then we have the cation radical, which is the complete molecule with just losing an electron, and it's positive. And so again, that's why it's detected, because it can go through the magnetic field. If it wasn't charged, it would just get lost in the instrument and not be detected. But then you can see here that if it's unstable, it can also break apart into its smaller particles. So here, C might break off, and you might have AB, or you might have BC, where A broke off, or you might break off to AB and then A, BC and then B. So anyway, this just shows all the different possibilities. And all of them will be on the mass spectrum to some extent, but how many of them will depend on how strong the bond is, how likely it is to break. So there'll be patterns, certain compounds and certain bonds break more easily than others, or less stable than others, and so you'll start to see patterns depending on the compound itself. So let's look at this example. If we have CH4, and if it's bombarded, now notice that CH4 will be our parent ion, or our M+ peak, which is right here at 16, CH4, 12 plus 4 is 16. It could lose one hydrogen, and so it could, if it loses one hydrogen, this will be 1, and this will be 15. So that's this peak here, the one at 15. We could lose another hydrogen, and then we have a peak at 14. You see that that's much less common than the peak at 15. And so what you're seeing here is, by the relative pattern, is that the most common ion is the methyl group, CH4. It comes through pretty much unscathed, but there's a fair number of the molecules that will have broken off one hydrogen. And so and keep in mind, these are not percentages that you add together, but they're just relative numbers. So the most common is the 16, but 15 is pretty common too. And then you can see that 14 is very uncommon. So it's not going to be nearly as likely to lose two hydrogens than it is to lose one hydrogen. This is also probably a really good time to talk about this peak here. Why is there a little peak just above 16? So 16 is our mass peak, and we have a little peak at 17. Well, sometimes this is called the M+1 peak, and it's due to isotopes. And so notice that it's very, very small peak. And so remember that carbon has, well, it's got 3 isotopes. So it's got 2 main stable isotopes, carbon 12 and then carbon 13. And about 1% of all carbon is carbon 13. Well, what's special about carbon 13? It weighs 13 AMU rather than 12 AMU. So it's going to have 1 more neutron in there and have a mass number that's 1 more. Well, if you had 100 molecules, one of them will be will weigh 1 more than all the others, just the parent peak, the CH4 plus will weigh 1 more, because 1 out of every 100 molecules will have the carbon 13 rather than carbon 12. So that's what's happening here. And actually, you can see here, it's about 1%, because carbon 13, since there's only 1 carbon, about 1 every 100 carbons has that mass of 13. And so you often will see an M+1 peak due to isotopes, and you can pretty much ignore it. Sometimes it gives an indication of how many carbons are in your chain, but for what we're doing, I don't think you really need to. You can pretty much ignore it, but don't let it confuse you, and don't automatically look for the highest peak. So in this case, the M+ peak is the 16, and the M+1 peak will be the isotope peak. And so you don't want to confuse that. And so when we do some problems, I'll try to make it really clear which is the M plus peak. And so then you can look for the other peaks. You'll see actually very much later on an isotope peak called the M plus 2 peak is actually can be very useful. So we'll talk about that in a little while. All right, so we can use mass spectrum in a number of ways. This first way that you'll see is not as common, or at least not in our lab. We don't even have a mass spec at all, so we're really just going to be looking at data that's been collected and analyzing it. But one way that mass specs can be used is to some of them can be very sensitive and can measure the mass up to 0.001 AMU, which means if you're given two samples with very similar molecular weights, you can distinguish between them by the actual M plus peak. So you can see here C5H2 has a mass of 72.0939 and C4H8O has a mass of 72.0575. So you could tell between the two of them. Now most of the instruments are much simpler than that, not as precise as that. And so the ones we'll be looking at, you'll just be looking at the whole number basically. But as you can see from some of the previous slides, then the splitting pattern can often give us information about the molecule. So this one, it's good to know, but not something we're going to use very much. And so the other way to use a mass spectrum, not quite as clear cut. So like I said, the values won't be that precise. We'll just really be looking at whole number masses. And then sometimes the M plus ion is not present, and so this would really prohibit using molecular weight to find an unknown. And then like I showed you, I sort of hinted at, sometimes we see a peak that's 1 or 2 above the mass ion, and that's due to isotopes. So again, I'll talk a little bit more about that in a second. So that can confuse the issue. You have to really know what your mass peak is. Just to give you a little comfort, whenever we're dealing with these kind of problems, I will always indicate, if the M plus peak is missing, I'll indicate it to you and tell you what the M plus peak should be, because we're really just going at the very simple end of things here. So we will use the mass spec to find a molecular formula. Sometimes we might have to find more than one. So, like we saw a couple of slides ago, 72 could be, I forgot what they were already. Well, you could go way back. So, CO2 versus C3H8, they both have a mass of 44. And so, if you know the mass peak is 44, then you can find out what are some possibilities for the molecule and kind of use that to figure something. Sometimes you have to just narrow it down to a few possibilities and then go from there. And then, like I also said, sometimes each compound has its own unique breaking pattern, and so sometimes that's going to be very helpful for us. But again, knowing sort of what the molecular formula or a couple of possible molecular formulas will help us. We'll look at common fragmenting, and then keep in mind that the positive charge usually remains with the most stable fragment, and so that's the one that's usually the tallest peak, the base peak, and that can also give us information about the stability of the molecule. There's a little video here of it's actually mass spectrometry that if you go to the actual PowerPoint that I have on Canvas, you can link to this and watch it. I also try to put the link on Canvas so that you can watch it. It's just a few minutes, and it's kind of telling you a lot of what I just told you. So here's just a few examples. We'll work through a few examples. So let's say we ran a mass spec and we find out that our M plus ion has the formula 110, and that's all we know about it. So how can we use that to find out what a possible molecular formula might be? So there's kind of a few steps that you want to go through. I guess you could type it in online or something like that, but we kind of want to, just get an idea here mathematically. It's not very hard because you may, I don't know, I'll just leave it there. So the best way to go about it is to take your mass number and divide by 12. So if I do that, I get 9. 12, why 12? Because that's how many carbons. So what is the maximum number of carbons I might have in this compound? Well, 110 by 12 is 9, remainder 2. So that would mean a formula C9H2, because the 2 extras would have to be hydrogen. Well, that doesn't seem like a very likely molecule, because how could you have, we learned about unsaturations, and you can't have that many unsaturations. So that's not a possible molecule. But remember that each carbon has a mass of 12, so that's equivalent to 12 hydrogen. So what if we take away 1 carbon and add 12 hydrogen? So that would be C8H14. That's a very reasonable compound. 8 carbon, it's going to have some unsaturations in it because 8 times 2 is 16 plus 2 is 18. So it's got 2 unsaturations, but that's a very likely, very good possibility for the molecule. Now, it might also have some oxygen in it. So keep in mind that 1 oxygen weighs 16. Well, that's equivalent in mass to a CH4 group. So you can replace a CH4 group with an O. So let's see, if we start with C8H14 and we remove a carbon and we remove 4 hydrogen, we get C7H10, and then we add an oxygen. So this has the same mass, 110. So C8H14 has a mass of 110, C7H10O also has a mass of 110. We could do another O. We've got a lot to work with here. So what if we take away another carbon and another 4 hydrogen? We get C6H6O2. So all of these 3 are possibilities, and that's kind of a good place to start, just to get yourself. Now, you might not sit here and go through every possibility because as I said way earlier at the beginning, you'll have other tools to use. Like, you'll know things about functional groups. You'll know things about well, I won't get into it, but you'll learn other things besides just the mass. So there'll be ways to figure out, is there an oxygen even in the first place? And so then we can so once we have it narrowed down to a few possibilities, then we can look at some of the splitting pattern, the pattern of fragments, and then, like I said, we can also look at some other tools that we're going to learn about later. An interesting thing that is important to remember is that nitrogen, now nitrogen itself doesn't have an odd molecular weight, but the nitrogen compounds, it's odd because it has an extra hydrogen. So this is not actually true. So nitrogen has, if a compound has a nitrogen, the molecule should have an odd weight if it has 1 nitrogen. So for example, if you saw a mass of 73, right away that should tell you that you have a nitrogen in the compound, because it's an odd number. It's not always absolutely true, but it pretty much mostly is true. So here we have an odd number. So we kind of go through the same process. 73 divided by 12 is 6 with a remainder 1. So, okay, it's possible to have the molecule could be C6H1, but that's not really a possible molecule. But if we take away 1 carbon and add 12 hydrogen, we have C5H13. That's not going to be a possible molecule either, because we know if we only have carbons and hydrogens, the hydrogen need to be an even number. So because it's odd, we know that there's going to be a nitrogen. Nitrogen is equivalent, since it's 14, it's equivalent to CH2. So what you can do is take away a C and 2 H's and put in an N. So this is a very likely formula for this compound, C4H11N. And if you're not positive, go back and add them together and you should get 73, right? 4 times 12 plus 11 plus 14 will give you 73. It's also possible that it has an oxygen in it, so it could be C3H7NO. There's not a whole lot of other possibilities. If you keep, I suppose you could keep going down to C2H3NO2, and that's a possibility, but there's only a few, as you can see. Now we're not doing huge molecules, so that's good. Now going back to the last example, the MZ of 110 is even, but it could have nitrogen. And here's the thing: if the total mass number is even and it has nitrogen, that means it has to have an even number of nitrogens. So most likely it's possible that it could have 2 nitrogen. So you can see that 2 nitrogen is equivalent to C2H4. So if you start with the C8H14 and replace 2 carbon and 4 hydrogen, then we can have C6H10N2. So that's also a possibility. We said the other one, CH8H14 or C7H10O. So anyway, you get the idea.